And I'm like, I could be studying.
All right, so we have some questions about the homework.
Yes.
Specifically, which
Well,
ones?
we our two tables. I don't know about these guys, but sorry I didn't talk to you guys. But we had a really concern and difficulty mastering 6.4.
Okay.
Section. We found 6.3 was manageable. 6.5, 6.6 was actually fairly simple.
Okay.
But we had a really difficult time with doing 6.4 problems.
Okay.
And one question that comes from is 125. I don't remember what page that is, but it's D equals 451. Yeah, 451.
Are we reviewing right now? Or are we doing?
It's
Yeah, we're going to do
I'm answering questions first, then we'll talk about the test.
because he said we take half the class for that. So.
Okay, so 125, drug medication problem?
Yes,
Okay.
yes.
So you have a formula that's given to you.
Which is D equals 5D negative 0.04H. And then I guess we're trying to find when D is 2, if I understood that.
Okay, so it says the formula blah can be used to find the number of milligrams D. So this is the number of milligrams. Of a certain drug that is in a patient's bloodstream H hours after the drug was administered. So this is your hours. When the number of milligrams reaches 2, the drug is to be administered again. What is the time between injections?
So if I understand, D is supposed to be 2.
Yeah, so they're saying they're going to give this patient an injection, start the clock.
Well, actually, my wife uses this formula, but I was like, well, can you help me? We actually use a computer for this.
Yeah,
I
we
was
just
like,
use a table
oh,
or something,
she's like,
computer.
We have an app for it.
An app, yeah.
I was like, well, thanks, sweetheart. And I was like, I can't cheat. I have to know this.
But you're right. We want to know when this reaches 2. Because when that reaches 2 is when you'll do it again. So we set D equal to 2. You get 2 equals 5 e to the negative 0.4h. And we're trying to solve for h. So h is like x. So you need to get that h down. So how do you get the variable down from an exponent? You use a natural log. Can I do it yet, though? I mean, this is the deal. It's a little tricky. We can do the natural log on both sides if all that's over here is something to a power. But I have a 5 in front. So I need to get rid of that 5 first.
Go up, but then I didn't.
I can't bring it up because it's not a log, right?
I kept getting stuck there.
So how about dividing both sides by 5? That seem fair? It just turns the left side into 2/5. And then from there, you can do the natural log. So I'll do the natural log on the left. Equals, and this is going to be real nice because when you do natural log together with e, those are special ones, right? They just kill each other off, and all you're left with is the negative 0.4h or 0.4.
Which that one, okay, now I understand how they got the answer now.
And then on this one, you actually have to do this on your calculator first. So you get your calculator out. Make sure you bring your calculator, not your phone. I can use my phone. So I'm going to do 2/5, right? 2 divided by 5, and then natural log. So I get negative 0.91632, whatever, is negative 0.4h. And then divide both sides by negative 0.4. Get about 2.29-ish.
Yeah. Well, that's what the answer was going to look. I just didn't know how on earth they got that because I was having a hard time.
With that
trying to
5?
dice with the
Yeah.
5.
You see it now?
Yeah, I didn't think about using algebra.
Okay. Now you know. And it's not that bad, right?
No. Which actually, I chose the more difficult of the problems. The rest of the problems I just should have been applying algebra as well.
So on the ones you might have further questions on, you think it's the same issue?
Some of them, yes.
I can go through anything else.
I had a problem with 109.
Same
Type of issue.
same section?
Yes.
Yeah, that's exactly the same thing. 5 raised to the 5e to the 0.2x equals 7. So you divide by 5 first and then natural log. So same exact setup.
Yeah. See, that's I got stuck and I was like, I didn't think. Because I saw the answer in the book, I just didn't know how to do it.
Do you want me to work 109 or are you good?
What's that like this?
This is
6.4.
If you don't mind.
Yeah, no, I'll do 109. So 5 equals 5e to the is it 0.2?
Yeah,
0.2x equals 7. Hey, come on through. So again, trying to get the x out of the exponent. So you got to drop it, but the 5 can't be there, so divide by 5. After you bring the 5 over, right? Yeah. 7/5 over here. Now natural log on both sides. Natural log of 7/5 on this side. And in the book answer, they actually don't even compute that. They just leave it. And then they write, over here they write 0.2x equals this. And they expect you to make the connection that 0.2 is the same as 2/10, which is 1/5. Isn't 0.2 2/10?
Yeah.
And so this is really 1/5 x equals natural log of 7/5. And then they multiply both sides by 5 to get the 1/5 out of there. That's how they come up with 5 natural log of 7/5. Now, if you just did it all in your calculator and got the decimal, that would be okay also.
Because I was like, because I saw the answer, but how are they on earth are they getting that?
The 5, yeah.
Because they converted the decimal to the
Mm-hmm. So remember, anytime you have a decimal, each one of those places means something, right? 0.4751. This is 4/10. This is 7/100. This is 5/1000. And this is 1/10,000. And you're just adding all those together. So if you just have 0.2, it's the same. 0.2 is the same as 2/10, which is 1/5.
Right. And
Is
then
it
they
okay
just
if we have
clarify.
it as a decimal?
Hmm?
Is it okay if we have it as a decimal?
Yeah, I wouldn't have cared if you would have left this as a decimal. Yes.
So when you put the natural log, it just disappears from that side after the exponent moves down?
Yes, but it's a property that we're using. They kill each other off. It's this property, natural log of e to the x equals x. That's the property we're using. Because these are inverse functions. E to the x, the inverse of e to the x is natural log. So when you put them together, they wipe each other out.
Yeah, it's kind of like when you go +1 and -1, it's not there. That's the way I kind of think of it in my head, so that way I remember. They just kind of
Yeah. Yeah, you're going to have to, however it makes sense to you, right, is the way that you want to remember it, but everyone's different. So what's technically happening there is that you're composing two inverse functions together. Yes?
On 6.2, number 59 was confusing me because I wasn't quite sure how to set up the inverse for it.
On which one?
6.2, number 59?
Okay. This is an interesting one.
Inverse for it, and I tried pulling out the math. The inverse kept on coming out to be the exact same as the original function, and I knew that was 16 had been right. So that's wait, it was
Is 69 or 59?
59.
We didn't have to do 59.
It's all right. Let's do it. You're supposed to find the inverse of this function, all right? So how do you find the inverse of a function?
You said everything, flip around all the variables, x and y.
Yeah, you first replace f of x with y, then you switch the x and the y. So everywhere you see a y, you put an x. Everywhere you see an x, you put a y. And then you solve for y. So I'm going to try and get y by itself. So I'm going to get y out of the denominator. So I'm going to multiply both sides by y.
You changed that from a 4 to a 1.
Oh, I did. I don't know why I did that. Interesting.
Whoa, wait, happened here?
Yeah.
That's
So
special.
multiply both sides by y,
I'm gonna do another dimension.
and that gets the y to go away on this side, and over here I have yx equals 4, and I'm just trying to solve for y, so I divide by x, and you get 4 over x.
Yeah, that's what I was getting to.
So your inverse is the same as the function. What?
Well, that's because it's an inverse function.
That's weird, right? That's kind of a weird looking thing. So let me try and convince you of what's happening here. First of all, you can't plug 0 into this, right? Can't plug 0 in? If I were to graph this without me going through too much detail, it would look like this. It's actually a rational function, and it would look like that if we graphed it. And then remember, what does the graph of an inverse look like? Reflection over the diagonal, like this.
Y equals x.
Right? Y equals x. If I reflect that, and check out what happens if I reflect that function. I get the same thing, right? If I just take this and just spin it over, it lands right on top of itself. And over here, same thing, it lands on top of itself. It is its own inverse. So you were right, good.
I was just going out like, wait a minute.
It sometimes could happen that a function is its own inverse.
That's weird. It's like your old grandpa or something.
I'm my mom and my dad. Okay, anything else that you want to talk about over homework? I am going to talk about reviewing for the test, but there is a topic that I'd like to make sure we have for the test. So one additional little thing here. Where is it? I'm not going to do that yet. Where the heck is it?
I don't like that yet part.
Yeah. Can we just take that out?
Let's just get your final as a final.
Yes.
We have to know everything about gravity for our final.
We don't need any. We don't need gravity. That's for losers. We need to use that stuff.
We need gravity the other day.
Okay, so what I'm talking about here, this is out of 6.8. This is going to be applications.
This is going to be on the test.
This particular topic will be.
What is,
This particular topic I plan on having on the test.
so we are doing 6.5 from.
Not the whole thing, just this one particular topic. All right, how many of you have heard of HalfLife before?
Yep.
Not the video game, because I think there is a video game called HalfLife too, right?
And the term of like chemistry, like uranium or plutonium has a
So,
half-life
so what
of
is it?
20,000.
Basically, over whatever the period of time is,
It's half of its
then,
life.
then it becomes half of what it was whenever that period of
Let
time
me slide by
starts.
you real
If
quick.
it's at 1 million, and a year goes by, it'll be at 500,000. Another year goes by, it'll be at 250, etc.
Yeah, let me take a couple of pieces of paper. Yes, that is exactly right. So you remember the example that I did where I took a piece of paper and then I cut it in half and then I did half again? And I did really good. I had one of my best performances ever. I got it down to like really tiny. Remember that?
We're proud of you.
Thank you. I felt good. So we're just going to adapt that just a little bit. What I'm going to do is I'm going to say, here it is, right? Here's the whole thing. Whatever it is, here's the whole thing. And then I'm going to count to 2. 1, 2. And then I'm going to count to 2. 1, 2. And then I'm do it again. Count to 2, 1, 2. Do it again. And then count to 2, 1, 2. Do it again. The half-life of that is 2 seconds. meaning every 2 seconds it goes down by a half. Now, if I waited a minute, then I'd be here for a while, right? I keep doing it after, a minute, then cut. Or I could wait a year, cut it, and then wait a year, and then cut it again, wait a year, cut it again, right? Or a decade, all right? So in chemistry and physics and biology, different substances on this planet have different half-lives. So you think about a substance like, trying to make an analogy, think of it like a campfire. If you've ever been like out to make a bonfire and you sit there, it's real hot, you do your marshmallows and stuff, and then you come out the next day, it's still hot, and maybe later on that night you go and you poke in there with, the coals are still hot in there. So it's really hot, and then it gets, less hot, but it's got this core that's still hot, you know what I'm saying? Eventually, it goes down to where its temperature reaches the temperature around it, right? That's kind of what a half-life is for substances like uranium, plutonium, different things. Carbon-14, everything has like half-lives. So the half-life is the amount of time that it takes for half of it to go away. Some substances, it's a few seconds. Some, it's a few minutes. Some it's a few days, sometimes it's thousands and thousands of years. But all of them are exponential decay. They're all exponential decay because it's half, 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 half. So we have a way of representing half-lives with a model. And so here's the model that we have. And I'm going to match with what's in the book. A of t equals a sub 0 e, do they use negative? No, good, to the kt. This is the model that we use for exponential decay. Exponential decay. What we will need for this is for k to be a negative number. If k is negative, this will decay. If k is positive, it's actually exponential growth, and then it doesn't fit into the half-life model, all right? So we need k to be a negative number for this to be exponential decay. Now, I just said half-life. I kept on doing half, half, half. Wouldn't you think that the base then would be half?
No,
No?
because that's the natural thing. That's the natural number, like it's found everywhere. So.
Yes, but me tearing, wasn't that first example I ever did, wasn't that, we did like, it did turn out to be like 1/2 to the x?
Yeah.
Well, the reason I'm not using 1/2 to the x is because, do you remember that change of base formula where we could change any log over to that other two logs? We can do the same thing with exponentials. We can take any exponential and change it over to base e. And because of that, we like to use e because our calculator has natural log on it, and it's just a standard base. We can model all exponential decay with this. All we have to do is tweak out the k, and it will make it look the way we want it to look. So we're going to figure out what the k is now. All right. All right. So let's work through this. Let's do an example. A bone is found and 0.56% of its original carbon-14 remains. How old is the bone? All right, this is what's referred to as carbon dating. You may have heard this before. We use this as an approximate way to determine how old something is. So there's a few things we have to know before we actually do this problem. When anything that's living, okay, has some amount of carbon-14 in it. So I have carbon-14 in my body, and I have a certain level of it, all right? As soon as I die, that carbon-14 starts to decay. As long as I'm alive, it maintains a certain level. So if I die right now, my carbon, like right here, like that, everyone's like, yeah, all excited. Okay, so we don't have to take the test, right? So, so as soon as I die, that carbon-14 starts to decay down. So if somebody finds my body, 1,000 years later, they can measure how much that carbon-14 there is, and they can determine when I died. But the key to it is knowing what the half-life of carbon-14 is. You have to know that in order to be able to do this. So the half-life of carbon-14, the half-life is 5,730 years. Oh, and there's some, I forgot to explain this formula, but I'll explain it as we move through this problem. All right, we good? That's it, that's all we have. We want to know how old the bone is. So remember when I was tearing the paper, right? Okay, after a certain amount of time, half of it was there, half of it was there, half. Well, imagine me waiting 5,730 years between tears. That's what the carbon-14, that's how slowly it's decaying, all right?
Your great-grandchildren's great-grandchildren.
My guess, my hunch feeling is that 5,730 years from now, I don't see anyone being around. I just don't see it. I don't know. I don't want to say I'm a pessimist, but I don't know. On Earth. Yeah, I don't think we're going to be hanging around here too much longer. We'll do each other in before we run out of resources. Yeah, we'll do each other in. We don't like to get along, right? We love not getting along, don't we? We love it. We're going to get all political and philosophical. Let's stay on track, okay? All right, so let me explain this formula to you. Here's the way the formula works. The formula works as follows. A naught is equal to the amount of whatever it is, okay? Amount of material, whatever it is, at the start. The initial amount. So the reason why they use A with a subscript of 0, A stands for amount, subscript 0 means time 0, starting time, all right? So A sub 0 is there, is what's there initially. Now I can verify that real quick. If I say T is 0, right? That's the start, I'm about to start my clock. If T is 0, this is 0, and e to the 0 is 1, and so it's just A sub 0. So at the beginning time, I have that much there, right? Right. T is time, and it's always measured in years. Always.
You lied to us with the paper example.
Well, then if it was so many seconds, right, I would convert those seconds to years. So, what's 2 seconds converted to years? It'd be very, very small. You would have to do that conversion. All right, that's what T is. The next part, K, is called the growth. Actually, in this case, it's called the decay constant. I'm going to say slash growth because if we make this problem an exponential growth problem, that K is going to be called the growth constant. It's decay in this problem constant. And that will always be determined by your half-life. Okay? So I'm going to put that underneath this. This comes from the half-life. We'll have to compute it, but I'm just telling you that's where it's going to come from. We will have to figure out what K is. And to do that, we will have to use the half-life. And then what's left? K, T, A naught, A of T. A of T is the amount of material at time t. So the left side of the equation just tells you how much of this stuff is there at a certain point in time. So when I say A of 0, right, that's going to be how much is there in the beginning? And we already said A of 0 would be A naught. Yes? Questions? All right, let's do the problem. What do we know? We know the half-life, don't we? Half-life? So let's work with that first. Let's try and get K. I said that's going to come from the half-life. So I'm going to work like this. Looking at this equation right here, I'm going to say I had initially 1 unit of whatever it is, carbon-14. Okay, so I'm going to say A naught is 1. E to the KT, right? Now, you know what? Let me do this. 1. How much do I want there to be? For the half-life, there should be half of it, right?
Well, 0.56% of it, yes.
Yeah, I'm not saying that yet, okay? I'm not saying that yet. Do you agree with the equation written like this? This means the amount that I have there initially is 1, which is like 100%. Yes, 100%. This is how much is there after a certain amount of time. I want that to be half. E to the K, how much time does it take for me to have half for carbon-14? Measured in years. 5,730, right? Do you see how that works? Half the material's there. We started with all of it after 5,730 years. So if someone came in and did a totally different problem and they gave me uranium, which maybe has a half-life of like 12,000 years or something, it would be the same setup, except that would be 12,000 whatever years. If the half-life was 1 year, then we replace that with 1. So this is how you get K for any exponential decay or growth problem. Questions? Continuing. All right, so this is going to be 1/2 equals E to the 5730K. And what am I trying to get here? K. I'm trying to get K. So check this out. This is why we did what we've been doing, right? You solve for K. It's up in the exponent. How do you get it down? Natural log. Can we do natural log right now, both sides? Yes, we're free because we don't have any number in front of E, right? Like the 5 we would divide through, but we don't have it. So we just go natural log on both sides. Natural log 0.5. I'm going to use my calculator, so 1/2 is 0.5. And then this side, what do I get on this side? 5730K, because the E and the natural log wipe each other out. And then I'll divide. So get on your calculator and do 0.5 natural log. So you should get something like negative 0.69314. The further you go with your decimal, the more accurate your answer is going to be. I'm just going to go to there, equals 5730K. And now divide both sides by 5730. And it's a really small number. 0.000. I'm getting like 1, 2.
Should we like do scientific notation or something?
No. 0, 9, 6, 8. Like I said, for these problems, the further you go, the better your answer is going to be. We should all be within a certain amount of each other, but you don't want to round this to 0.001. And you certainly don't want to round it to 0. You don't want to say, that's close enough to 0. Right? We need as many digits as possible. But don't go over like 15. Okay, don't get crazy on me.
But then it'll be more accurate.
It will be more accurate, yes. Okay.
Everyone's like finishing the test, and I'm like, all right, just finish writing out that number.
So here's what we've got. Here's what we got. For this particular carbon-14, I know what this constant is. So I can rewrite this formula and I can replace the constant with negative 0.00012096 T. And this right here is the master equation that we have for carbon-14. Now, let's talk about our particular situation. Tell me about this bone. We found it.
It's got 0.56%.
0.56% of its carbon left, right? So the amount that we found it with, the amount of carbon-14, when we found it, is 0.56%. I need to convert that percentage to a decimal. 0.0056, right? That's how much I found. How much of it was there initially to start? 100%. So this is now, okay, when I found it, right? When it started, when it died, right? How much did it have when it died? 100%, right? Which as a decimal is 1, right? 1 is... Do you understand what I'm doing? So this right here is the initial amount, A sub 0. This is how much it has at a certain point in time. So what I know is that this right here starts out as 1, and at some point in time, the left side turns out to be what? 0.0056. And then the only thing I have left to solve for there is t. Do you follow that? Okay, so we're going to write that down now. Here's where I'm at. The left side of the equation is 0.0056 must equal 1. I'm not going to write the 1. E to the negative 0.00012096 T. And I'm going to solve this time for what? T, right? Natural log again, right? So we use the, do you see, we use the half-life to start the problem. We use half-life just to get K. Once we have K, then we can do this problem for any value of carbon that we find. So natural log of 0.0056 equals the right side natural log kills off. We get negative 0.00012096 T. And now, get your calculator out.
Negative 46.29323457.
Are you getting, on this side, are you getting negative 5.18498? Anyone getting something like that for this? Equals negative